All right, good morning. We are recording, and let me take a look at who's here. That's not that many. 16 according to this. And let me minimize that so it can work in the background. I'll wait about another minute. So what I'll do, the first part is I will complete what I had intended to do on lesson 17, and then my stuff started locking up. And then we'll go to lesson 18, which is actually comparatively short, although these are 16 and 17 on the Blackboard server. I believe I've already made the links active. Oh, no, I haven't. Done. And I have also made the lab available. Check. And there's an uploader there this time. So I took care of that. And at the end of lesson 18, which is really 17, we'll go into lab. So you have more time today for laboratory. Farhang's patience and willingness to start early is kind of the guiding principle of that. So use today because there'll be extra lab time to your advantage. All right, so we're 2 minutes in. That's enough time for everybody that's going to show up. And let's begin. If you recall, at the end of last time, I'd introduced interval estimates, and we'd looked at this example where we had two sets of samples, the blue set and the orange set, and they turned out to have, for all practical purposes, the same mean value, but they're clearly not the same. And if we were to assess which one is a better estimate of the mean, so the mean value is around 50, we would be much more comfortable saying that the mean of the orange stuff is 50, less comfortable saying the mean of the blue is 50 because there's quite a lot of range in the blue values. We showed that they were not normal and so forth. And then I went into percentiles. Well, actually I have to run all these things. So let me work through them a bit at a time. So naturally my picture is going to change. Oh, actually it came out better. I like that picture better. Get past the percentiles. Go to the exam scores. Okay, so we're kind of where I wanted to be. And last time, what I wanted to do was take advantage of the histogram making capability of the data science module from the Data 8 textbook. And so we got to quartiles, and I think that's where my stuff stopped working. Okay, so let's go back to the city of San Francisco, the overpaid government employees, at least at the mayor's level. We have a large database. $43,000-ish rows, and then we went ahead and pulled out the mayor. There's only one mayor, so we can learn about the mayor's compensation. We can sort the compensation of everybody by the dollar value of total compensation. We have some negative ones which make no sense. So what we're going to do is extract out the ones that were over $10 an hour. I guess I should change this to, what's the new federal minimum wage? Is it 13 or 15? I need to change that, but not right now. So after we do some cleansing of the underlying database, we're down to 36,000 rows. And let's go ahead and look at a histogram of those 36,000 entries. And so we're going to build a histogram going from 0 to 700,000 with 25,000 unit-wide bins. So every bin represents a $25,000 increase in total compensation. Oh, and it worked. And so now if we look at that, let's see what this histogram is telling us. From that histogram, how many employees make more than $600,000 per year?
Almost zero.
Almost zero. Yeah, less than one employee. So correct. From the histogram, what would you say is the most common compensation package?
120,000.
Yeah, in the $100,000 to the $125,000 category has the tallest bar. And what is that most common compensation known statistically? What's the statistical name for that pointy part?
The median?
No.
Oh, the mean.
Nope. One more try.
Wow.
It does begin with M, so you have the first letter of the name.
Wait, the most common? Oh,
Yeah.
the mode.
Correct. It's easy to remember because you want to put ice cream on it, and so you have a la mode. So the median would be the value where that. I am so glad you're muted. That looked like a really healthy sneeze.
That was you.
The median is the location where that distribution would balance. If you moved a balance beam from left to right, where it exactly balances. So what's your best guess of the median from the picture? Absolute silence. Silence.
Best guess, in my opinion.
Yep.
It's, I also say the 100,000 to the 120,000.
Okay, that sounds
again.
good to me. And that's what I'm after. And so what you did is you mentally kind of split that thing into what looks like would be a half, in the sense that if you were trying to make it balance on a rod, where that rod would have to go. And the last thing is we can estimate what the median value is, and it too will be somewhere 125,000. So what we find out is most of the values are below 300,000, but there are a few that are a bit higher. There is one person called the Chief Investment Officer who's compensated at $650,000 and takes all the money from the various people that work at the city and invests it for them. And he invests it in the It's My Pocket Fund. There's also the medical examiner's office. They're pretty highly compensated, because taking people's money for retirement and going and determining how stiffs died is very highly compensated jobs. So now let's go ahead and find out what the median. Remember when I asked you to guess from the picture, you guess between in the $100,000 to $125,000 category, and sure enough, your visual guess was quite good. In fact, we can look at the entire population and find the population median. I'm going to need that later, so let me run it. I think I'm going to need that later, so I'll run it too. Now we're going to take from that 36,000 record database, we're going to sample 500 employees at random without replacement. Without replacement is a very Stalinist method of sampling. So if you remember, Joseph Stalin had a method of sampling his population. He would take someone out of the population, shoot him in the head, toss him in a ditch, and then tell the rest of them, quit misbehaving. It was very effective. So that's without replacement. With replacement would be they take them out of the line, they'd slap them, and then push them back in the line. But I guess he had no shortage of people at the time. So we got a little bit of a political commentary there from 40 years ago, 60 years ago, or more. So we're going to sample 500, and we're going to use the category with replacement false. The sample function is derived from the NumPy function of similar name, but it's a property of the data science module. And then from our sample, we're going to select the total compensation key, and we're going to generate a histogram of that. And then we're going to make an estimated median using the percentile function, which also is derived from the data science module. And then we'll print the estimated median and compare that to our population median. Our population median is known because we have the whole population. So we're going from God mode to man mode. So we take a sample. Here's our histogram of our sample of our 500 employees. And the estimated median is 108,000 compared to the 110,000 population median. So as estimates go, I would say that's not terrible. And if we compare the appearance of the two histograms, they're not the same, but they look enough alike that we might conclude that is a pretty good sample. In this case, our sample size is relatively large, so that the distribution of the sample approximates the distribution of the population. Consequently, the sample median is not very far from the population median, although it's not exactly the same. So now we have one estimate of our parameter of median. But if the sample had come out differently, the estimate would have a different value. And what we want to do is to be able to quantify the amount by which the estimate could vary from sample to sample to sample. In this case, sample being the 500 without replacement. And that measure of variability will help us assess how accurately we can estimate and report the parameter. So to see how the estimate would be different if the sample had come out differently, we could draw another sample from the population, but that would be cheating. So what we're trying to do is mimic real-life sampling where we don't have the entire population. So we sample from the population once, and now we have to get some other random sample without sampling from the population. And one technique that has emerged as useful is called bootstrapping, or the bootstrap. There's another one called the jackknife. So the statisticians are very weird people because they spend their times with boots and knives, hence the reference to Stalin earlier. In bootstrapping, from the original sample, we will resample from it. And there is a fundamental assumption that's occurring when we do that, is that the original sample is comparatively representative of the entire population. So let's play a mental game. If the original sample only took a single value from the population. So instead of being 500, if the original sample was a 1, we get a very different result. The median of that one value is 73,000. Now looking at that histogram versus the population histogram, is there anything about them that's alike? That'd be a no. The only thing that's alike is they have vertical bars. But a sample size of 1, we already know is not a very good sample size. We could go bigger. Let's take 10 samples. And maybe you could argue that's doing a little better, but those two histograms are so unalike that we would be fools to think that our sample in any way, shape, or form approximates the population. And we still see that our median estimate is quite low. If we go take 100, now those are starting to look similar. Our median is still low, and the example we're using is to take 500. At 500, the distributions look a lot alike. Bearing in mind, in actual analysis with real data, when we may not have the luxury to go look at the population distribution because we may not have it. So as long as the sample size is large enough that we're comfortable with stating that that sample is representative of the population, we'll now treat that exact sample as the population. So we pretend that that is the population, and we can take random samples from it until the cows come home, or hold our breath until our eyes turn blue, whatever metaphor you want to use. Actually, those aren't even metaphors or similes. I never metaphor I didn't like. So what we're going to do is use our large random sample from the population as the population. And this allows us to lift ourselves up by our own bootstraps, and the sampling procedure can be replicated by sampling from the sample. So the steps of the bootstrap method for generating another sample are pretty straightforward. So we've got our original sample from the population. We're now going to declare. We take our finger and we point to that original sample and says, you are now the population. And once it does that, it changes the color of its bars from a nice comfortable green to a scared red. And then we're going to draw at random with replacement from that sample the same number of times as the original sample size. And we'll save that result. We'll calculate a statistic on it, in this case, the median. And then we do that again and again and again. And we do it as many times as we need to. It's important that resampling is the same number of times as the original sample because the variability of an estimate depends on the sample size. Since our original sample had 500 employees, our sample median was based on those 500 values. To see how different the sample could have been, we have to compare it to the median of other samples of size 500. If we drew 500 times at random without replacement from our original sample of 500, we would just get the sample back. But by drawing with replacement, we create the possibility for the new samples to be different from the original, because some employees might be drawn more than once and some others not at all. And that begs the question as to why this is a good idea. For one thing, it's the subject of today's lesson. More importantly, because the distribution of the original sample is likely to resemble the population if we took enough instances, and the distributions of all the resamples are likely to resemble the original sample, then by essentially an appeal to the transitive axiom, the distributions of the resamples are likely to resemble the population as well. So that last statement appears to be quite subtle, but it's actually appealing to set theory that you got back in that mathematics class. Although I'm not sure mathematics is taught by live human beings anymore. You probably take it on a computer program. But the transitive property is if A is related to B and B is related to C, then by the transitive axiom, A is related to C. And we know it exists for equality and a few other things. So we're building upon that principle of logic and set theory to defend that the resamples represent the original population under the transitive axiom that the original sample represents the population. So let's go ahead and make a resampling. So we're going to create an object called resample1 because I'm very uncreative in naming. And we're going to take from our sample a sample, and then we will produce its histogram. We'll compute the median of the resample and report it. So when we run that, this is our first resampling of our initial sample from the population. So take a look at that picture. Let's see, maybe I can use my screenshot to keep track of all these. This usually comes out to be a disaster, but there we go. So I'm going to keep that up there. Hopefully this will let me do it again. So there's our resample. Here's our first sample. And I'm grabbing enough words. Oh, you piece of crap software. Never mind, it clobbers the instances. I miss the old screen capture stuff, but Apple, in its infinite wisdom, had to screw up a perfectly good thing. Here's our population distribution. Burn that into your memory. Here's our first sample distribution. Not identical, but they have roughly a similar appearance. Here's our first resample distribution. So the resample came from the initial sample. There's what the resample looks like, and there's the population appearance. So they are preserving each other's general appearance. So now we have a second estimate of median, $111,101.19. Just doing a single resample is silly. We can make a second one. Oh, that one doesn't plot because I don't have it plotting. And what we want to do now is use our simulation principles that we studied earlier in the class. Remember, we simulated rolling dice and playing Russian roulette the only safe way, which is to play it on the computer using your head and my finger on the revolver. That's the only safe way to do it. We play it in the computer. Nobody has to incur the consequence of game over, meaning game over. What we'll do now is we'll make a function that we define that takes a sample, samples from that sample, calculates the median, and stores it in a object called replications. And so what we will change, replications is how many times we want to bootstrap. So replications could be 1, 2, 200, 2,000, whatever. Here's the function. So we have original samples input. We have a label, which is going to be essentially a string variable that we will use to keep track of things. And we'll have the replications. So you think of the label as a key in a dictionary. These aren't dictionaries, but it's playing the same role. So from our original sample, we're going to select based on the label. We're going to place the contents into an object called just one column. Then we're going to make an array called medians. At this point, those are all empty. And then we're going to go from I up to replications. We'll bootstrap the sample where we take the just one column object, we resample from it, and store that in an object named bootstrap. Then we compute the median of that sample, essentially resample, and then we store it in an object called medians. And when we're done, we're going to return the value of medians. So that is all this function does. It's harder to explain than it is to actually look at it. And this was from the original UC Berkeley script, but it's been modified to actually work. Hopefully it will work and not embarrass me on camera. Now we'll replicate the bootstrap process 5,000 times. So instead of putting all that into a for loop, going from 1 to 5,000 and figuring out how to keep track of different values, we just created the bootstrap function. So we're going to have an object called bootstrap medians. We'll run the bootstrap median function that we created. We'll supply it with our sample. We'll use the total compensation key as the label to search for. And eventually we're going to do it 5,000 times. But first, let's just do it 5 times. So essentially, it's going to do our sample, resample 1 through 5. So it doesn't take it very long to do 5 times. BSTRAP underscore. So here I'm going to go look at the contents, and I should have 5 values. So our first resample, we got a median of 110,000. Whose short-term memory remembers what the population median was? The true value.
Didn't we say it was like 125,000?
I'm gonna
Or
go up.
110.
I'm gonna go up and look because I don't remember either.
It was 110,000.
It should be right here. There we go. The population median is 110,300. So our first resample estimate, 110,700. Next one, 111,300, 111,600, 106,600, 114,700. Let's now do 5,000 estimates. That takes a little bit of time. Well, I really should have timed this before class. Okay. So now we have our 5,000 estimates, and let's go ahead and build a histogram of the estimates. So this histogram is going to be a histogram representing our estimated medians. No longer the estimated compensation, but the median values. Because we know what the population median is, we're also going to plot its value on the picture as a red dot. And I'll make it a big red dot. Hopefully that doesn't clobber everything else. So here is our population value. That's the true value that in real life we never really know. Here are our bootstrap estimates. And would you say, looking at that our distribution of estimates is relatively reflective of the population value?
Pretty much spot on.
Correct. So keep in mind that the red dot is fixed. And if we were to report that the median compensation for this database is between 100,000 and 115,000, I'm leaving a few of these pieces off the end just for the sake of discussion. In 5,000 resamples, our interval that we just reported contains the true value. And that is the whole idea of an interval estimate. We'll be computing intervals, and then we want to be able to assess the probability of essentially a type 1 error on those intervals, the chance of reporting an interval that by coincidence happens to not contain the true value. We want that chance to be small. If we want that chance to be really small, what does that do to the size of our interval?
Decreases it.
Did you say increase?
Decrease.
It increases it. You're exactly opposite. If we want the chance, for instance, if I want to guarantee that I get the population median of this database, I'm going to report the median value is between 0 and $10 million, because 10 million is an absurd value for this database. My chance of that interval not containing the true value is quite small. In fact, it is arguably 0. If, on the other hand, I wanted to report an interval that the median value is between 110,000 and $111,000, not knowing where the red dot is, which we do in this case, that's a $1,000 range. So the chance of me reporting an interval that does not contain the true value in that instance is quite high. So if the probability of an interval not containing the value, if we want that probability to be high, the interval has to be quite wide. If we're willing to accept some risk of being wrong, the interval gets narrower. It's kind of opposite to how the language, the English language, prevents it. A confidence interval that's very wide, you report high confidence because the chances of you being wrong in that interval are quite small. It also means that you can't narrow down a value at all. But a narrow confidence interval can be achieved either by accepting greater probability of being wrong or by taking more samples to reduce the variance. So going back to our picture. In the picture, keep in mind the red dot is fixed. It's the population median. The empirical histogram is the result of random draws. So it will always situate randomly relative to the red dot, although it's pretty darn close here. Also, remember the point of these particular computations was to estimate the population median, which is the red dot. Our estimates are all the randomly generated sampled medians whose histogram you see above. We want those estimates to contain the parameter. If they don't, then they're off. So we want to assess now, do the estimates capture the parameter? Or more appropriately, how often is our empirical histogram of the resampled medians sitting firmly over the red dot, not just brushing it with its tails? To answer this, we have to define sit firmly. So let's take that to mean the middle 95% of the resampled medians contains the red dot. If we make that statement, we can calculate the two ends of our resampled medians. So we can calculate an object named left, which is the 2.5% percentile of the bootstrap median object. And we'll create an object called right, which is the 97.5 percentile of the bootstrap medians. If we add 97.5 and 2.5, we get the full 100%. And so 2.5 twice is 5%. And so we're trying to represent the upper and lower bounds of the 95% sample range. We do that. Our lower bound is 101,000. Upper bound is 113,000. If we go look up here, 101,000 is down here. 113,000 is up here. And in that particular instance, those upper and lower bound that 95% of the sample range does indeed contain the population median. So if we want to now represent that interval and the median, we'll plot them below. Let me get the size up to something that's, let me see if it can handle a 3-digit character. So red dot is our population median. The yellow bar is our 95% interval based on 5,000 resamples. So that interval estimate in this instance does indeed contain the population value. We could stop there, but the question is, was that a fluke? Did we just get lucky? What we want to do is see how frequently an arbitrary interval contains the parameter. And to do that, we'll run the process over and over again. And specifically, what we're now going to do is we'll do the following process 100 times. We'll draw an original sample of size 500 from the population. We'll produce 5,000 replications of the bootstrap and generate the middle 95% interval of the resampled medians. We'll do that 100 times. When we're done, we're going to have 100 intervals, 100 yellow bars. And then we're going to count how many of them contain the population median. And that kind of sets up the process for how everything is done with regards to interval estimates. So first I have to do the big simulation. So let's see, what time is it now? 10:36. Go ahead and see how long this thing takes. It takes 4 minutes on the Amazon Web Services server. I'm running on Raspberry Pi 4 right now. So we can produce an array called left ends, an array called right ends. We'll start with the total compensation database. We'll produce our first sample, and then we'll produce medians based on bootstrapping the first sample 5,000 times. We will append to the left end and the right end objects the computed left end and the computed right end of the medians that we just calculated. We'll do that 100 times. And then when we're done, we will produce an object named intervals, which will be a table with columns, and we can look at those columns. I think I can run that and it won't break anything. So I'm going to run that and let this run in the background. And this now takes longer than most of what you're probably accustomed to. But let's ask ourselves, why does it take so long? Think of what
Just
it's
time.
doing. It's having to resample and do calculations 5,000 times per resample, and it's going to do that 100 times. So it's going to do the resampling 500,000 times. So it's got a little bit of work to do. While it's running in the background, let's pretend this is the output for the sake of discussion. And when this changes from busy to idle, I'll know it's done. We have our population median. And what we might want to do is, once we have computed those intervals, we can count how many of them contain the population median. So we can look in the left collection, count the number that are below population median, conditioned where the right is above population median, and then count the row numbers. And in that instance, there were 94 of those intervals. 94 of the 100 actually contained the population value. In general, we expected 95 of the 100 intervals to be good ones. They will contain the parameter. It's hard to visually show all the intervals on the horizontal axis because they have quite a bit of large overlaps. And so instead, we're going to generate a graphic where we plot an interval and we just give it an identification number, number 1. Then we plot the next one. It has identification number 2, and so on, all the way up to 100. And then each of those identification numbers is plotted on the y-axis. So we're going to have a collection of yellow bars all stacked upon one another, kind of like a Jenga stack. And then we're going to have a vertical red line that represents the population value. And so here's the result of doing that. So our first interval down here indeed contains the red value, so that's a good interval. Second, third, fourth. So we go here and let's just count the number of failures. So this 95% interval right there was a bit left of the population median, does not contain the value. So that one's a failure. This one up here is a failure. That's 2 failures. This one's a failure. 3, 4, 5, 6. So 6 of the 100 bootstrapped interval estimates failed to contain the population parameter. So we had a 94 percentile 94 of the 100 contained the parameter. To summarize what we saw, suppose we're trying to estimate the population median by the following process. Draw a large sample, bootstrap the sample, get an estimate from the new sample, repeat the step thousands of times, get thousands of estimates, pick off the middle 95% interval of all the estimates. That gives you one interval of estimates. Now, if you repeat it 100 times, 95 of them will contain the parameter. In other words, the process of estimation that we just proposed captures the parameter 95 out of 100 attempts. And so we use this principle to quantify the uncertainty of our estimate. We don't actually do the 100 runs because that's, especially on a big database, that's a real waste of time. We instead use the underlying principle and we say, I have a 95 in 100 chance that my interval estimate is going to contain the true value. I'm going to go with it. And that is the essence of interval estimation. So the big simulation is still running. How far into it? Let's see, 38 and 43 is 2, that's 5 minutes. So I don't know how much faster the Xeon processor at Amazon Web Services runs than my Raspberry Pi, but at least double. So I'm going to wait that out because I actually am curious to get the time value. Let's get back to this picture. Without details of the actual numbers, is it clear what this picture is representing?
Yes.
Okay, so I got a yes. Let me ask you guys some questions. What does one of these yellow bars represent?
They represent a sample of the
The-
population where it probably drew more of the sample from the latter right side. So it drew more what's it called? It drew more samples. It drew more numbers from the upper half of the population.
In that instance, okay, that's quite close. The bar is an interval estimate taken from what? Where did it derive its original data? Two possible answers, the population or the sample. Where did it derive its original data?
the population? Or is it-
The bars actually came from the sample. And the bars, are they actual data, or are they a statistic based on that data that is taken from the sample that is taken from the population?
Statistic.
It's a statistic that is taken from the sample that is taken from the population. Because if you recall, when we plotted the entire population, we had a range from 10,000 up to 700,000. And the only way we could get this a plot of this narrower range is we're no longer dealing with the original range, we're dealing with a statistic on the range. So in this particular instance, that statistic was the median. However, this same process can be applied to other statistics. It could be applied to the mean, it could be applied to the variance, suppose it could be applied to the skew, and we can use that to construct intervals that in large enough sample size are guaranteed to approximate our 95% reliability. So this is the method by which estimation reliability is reported. That
I have a
guy's
question.
still grinding away.
Based on what we did today, what were we looking for? Like, were we trying to figure out whether the sample accurately measured the population, or what?
We
Like,
wanted,
overall, just what have you been looking
we
for?
wanted to compute a median based on the sample and assess the reliability of that estimate. Because if we just compute a median from a sample, we get like $109,000, and you're betting your life on it. So you want to know how good that estimate is or how poor. So rather than betting your life on just one number, you negotiate with the hangman. If I report a range, we accept that. And so we're now reporting a range. I think that the population median lies between 100,000 and 120,000, with a 95% chance of that interval actually containing the true median and a 5% chance of failure. So that's what we're searching for with interval estimates. Is this guy still running? Well, let's see if I can crash my little computer. That shouldn't be too hard. Let's move on to lesson 18, which is actually what we're supposed to do today. Although 18 I think is 17, because 17 is 16. Damn Python counting. So we're now continuing with interval estimates. So we just saw an example of the median. Let's take this example and move a little bit forward with it. So the confidence interval for a true population median can be computed in a couple ways. One, without assuming the data follow any specific distribution, or assuming they do follow a distribution. Let's look at a non-parametric estimate for the median. We'll do one based first on the binomial distribution. The second one's the bootstrap method, which we've already seen. The key thing to the bootstrap method is it's general for many estimation problems. If you can't figure out a way to do it using something like a binomial or Poisson distribution, these are discrete distributions, then the bootstrap will always produce an estimator. But the bootstrap, cool. So this took 1049. So what's 38 plus 49? It takes 11 minutes. So now if I do everything, oh, I actually, in that instance, I got 97% success. And there is the bootstrap that we just did, took it 10 minutes. There's one failure. Most of the estimates are quite high. The interval's high. Here's a failure where the interval is low. Here's another failure where the interval's high, and the remainder all contain the population estimate.
So what's the difference between the different shades of colors?
Oh, what do you mean?
Like how some of them are kind of like a green, and then some of them are kind of like a yellowish.
That's your computer, because to me they're all yellow.
Oh,
See it too. There's I see them both as yellow, but the very top is a darker yellow, and then it gets lighter, and then darker, then lighter, then darker, then lighter.
Let's try a different color. Let's see, blue is an RGB, that's a primary color, so that should come across. How about that? Although that's a little bit hard on the eye with the red line. Do those lines all appear blue to you?
Not all the same shade.
That's your computer. There is no significance to any shading. It's just how your computer is rendering.
Dr.
the
Cleveland, do you
image.
think we can change the aspect ratio and maybe get a bigger plot?
Let's see, row, column. Let's try to make it double wide. Hopefully I did that right. Oops, I changed the wrong one.
But now we know that they're all the same color.
Oh, they come out the same color that way?
Yeah, I think some of the lines were getting pressed together, so they would come out as darker. But I never knew that people can tell the difference between yellow and gold. Thank you.
So those should all look the same color. Is that
Okay.
an improvement? There's slight
Yeah.
shading differences. Anyway, graphics are to enhance our understanding. You can use color as a fourth variable in many instances, but I would suggest that you never depend on that, because using color as the fourth axis has pitfalls, as we've just demonstrated here. Because for instance, that line and that line, I have two of them right next to each other. I will confess they look slightly different shading to me, but my brain is accustomed to colors being wrong, so it doesn't, I don't pay any heed to that. All right, returning to lesson 18. Actually, let me be sure I saved that one. I'll leave the aspect ratio all screwed up.
I have one question before we continue.
Mm-hmm.
What is CDF?
Cumulative density function, or California Department of Forestry, depending on context, but this is definitely not a firefighting notebook, so cumulative density function. There's a cumulative density function right there. You've seen them before. We called them something else, Farang. What do we call them? Empirical distribution function.
CDF, or yeah, empirical
But
distribution.
it's cumulative density function. So first, let's look at a binomial approach. In the binomial approach, we start out by choosing a desired significance level alpha, which is the risk of not getting the true median. That was our 5%, 95%. And we assign 1/2 of the risk to each end of the interval. So again, alpha represents the probability that the interval we compute will not contain the population value. Ironically, we'll never know with a real instance. To compute the confidence interval for that median, we will use the cumulative density function of the binomial distribution. And we can learn about the cumulative density function at skippy.org, and I will actually take the link, and it's a standard .org sheet. Usually when you see something that's .org, the information is absolutely useless, but I was looking for a cumulative density function, and somewhere down here, there we go. And that's all I needed. Then we go back to our notebook and we start to build our script. So we're going to need NumPy, pandas, Skippy stats, and the plotting library. We're just going to plot what the cumulative density function looks like. We'll do 25 binomial experiments. We'll set the probability of a positive outcome to a half. So essentially we're flipping a coin 25 times, and then we're going to keep track of the heads each time and plot the resulting probability distribution function. So I'll run the script and I should get that same picture back unless it's... So this tells me that in 25 experiments, I will see all the possible random variable outcomes, but in fewer experiments, I have very little accumulated probability. And so what I want to now look is I want to use this distribution, and let me get the random variable value. Our random variable is either 0 or 1, and in 12 flips, we roughly can account for 50%. This axis is not quite right. To determine the 100 1 minus alpha % confidence interval, we'll use the distribution function to find the critical values of the ranks of the data set that correspond to alpha over 2 and 1 minus alpha over 2 points on the binomial cumulative distribution function. These critical values of the ranks are then associated with their data values to form the upper and lower confidence limits for the median. We then use the binomial distribution to answering the following question. How likely is it that the true population median, C at the 50th percentile, would be such that in K of the N observed data, it would be above the 50th percentile and N minus K below the 50th percentile, where K could be 0, 1, 2, 3, up to 25 out of 25. The binomial distribution with probability of half is used because the probability of being above the population median is 50%. Probability being below is 50%. The resulting confidence interval will reflect the shape of the original data. Non-parametric intervals cannot exactly produce desired confidence levels when the sample sizes are small. That's because the possible values are discrete, jumping from one data value to the next at the end of the intervals. However, the confidence intervals close to those desired are available for all but the smallest sample sizes. So the process of computing the confidence interval is best illustrated by an example. So we're now going to just plunge into an example. Let's suppose that we made some measures of arsenic in groundwater in southeastern New Hampshire, and the 25 arsenic concentrations are stored here in an object called arsenic list. Let's compute the 5% interval estimate for the median concentration. So here's our list. And let's go ahead and just make a box plot, because the box plot gives us a lot of visual information. What's this lower horizontal bar here?
Your minimum value.
These 3 dots up here?
Outliers.
We should have given you guys a different name. Yeah, these ones are so far away from everything else that they look like they don't belong. But they're not really an outlier until we apply an outlier identification test, which we haven't even talked about. What's this horizontal bar up here?
Your maximum.
Excluding these out and
Yeah.
outliers.
Yeah.
This orange bar right there.
Your median.
Median. That's kind of what we're looking for. And it probably has a value of around 19. What's this bar up here at the end of the box?
75th percentile.
Good. Low end of the box.
25th.
Excellent. Farang has done a good job in coaching you how to interpret box plots. So if we compute the sample median for this list, it will come out to be a value of 19, which happens to correspond to the 13th observation, ranked from smallest to largest in this sample of 25 things. We can now use the binomial distribution to determine the 95% confidence interval for whatever the true median is. So all I'm doing is regurgitating what I just read to you. Sample median value, NumPy percentile, arsenic list, pull the 50th percentile. NumPy sort, arsenic list, put the sorted value back into the list. Index value 13, and then we're going to print the 13th element of the sorted list is, and we print the 13th element, and it says element 13 is 19. Now to use the binomial distribution, we need to obtain the critical values from the cumulative binomial distribution function by creating a list of binomial values of the correct length that represent these index values, this element 13, if you will, and then pull the index range that corresponds to the closest we can get to a 95% interval estimate. And then from those indices, we access the data and report that. So N, in this case, is going to be the length of our arsenic list. The probability we want to assess is the 50th percentile because that's the median. We have a couple of empty lists here. And for a random variable going from 0 to n, we'll float it and store that value in x, and then we will append using the Skippy stats binomial cumulative density function that random variable for a binomial distribution with n things, probability of p, and then we will append x to this object called rank. So what we're going to do is associate rank and probability with each other. Where have we done that before? Rank of things.
Is it the Weibull?
Good. It's actually all the plotting positions are doing that, is that we're associating the rank of something with a probability. So Farang has also done a great job there. Then for a random variable going from 0 to n, if the probability, the return probability based on the binomial distribution is bigger than 0.5, we store that value in lower. We keep track of the rank of low, and then we break out of that loop. So this is the first time we have seen breaks used usefully. And if the probability of the random variable is bigger than 0.95, we declare that an upper, and we break out of the loop, and then we're going to count how many things are remaining. Then we'll take an estimate of the median based just on the arsenic list, and then we'll produce a 95% confidence interval of lower and upper. And that's based on this conditional computation. And then we'll get the actual interval probability because we can't hit 95% with 25 things. So let's let her rip. Okay, estimate of the median is 19. Our interval estimate, where we have a 95% chance of containing the true median is between 4.8 and 100. The actual interval probability for that range for 25 items is 92.4%. So our tool isn't actually bad. So the code indicates that the upper and lower confidence interval occur at ranks 7 and 16, and these translate to concentration values of 4.8 and 100. The 8th and the 17 values in the sorted list of concentration values. Because the sample size is small, we know the interval will not be an exact 95% confidence interval, and we computed the probability that the interval would contain the true value using the cumulative distribution function. These results tell us that the true probability for that interval estimate is 92.4%, which is close to the desired probability of 95. And thus one can say that the closed interval of 4.8 to 100 is the best approximation to a 95% interval estimate for the median for these observations. An alternative to binomial distribution-based approach is to use bootstrapping, which we've already seen. It's one of many of the computer-intensive methods that uses observed data to represent the probability distribution from which the data were drawn, rather than assuming a normal or other theoretical distribution. Because it has robustness and coverage accuracy, the bootstrap method is often preferred for computing an interval estimate, especially if the data are skewed or the underlying distribution is unknown. The method works pretty well for data that do follow a specific distribution. In that case, it returns interval endpoints very similar to those based on the distribution, for example, t-intervals for the normal distribution. And we've seen our bootstrap method before. It consists of repeatedly resampling from the data set with replacement. And the term with replacement means that each observation that has been selected is put back into the data set so that it can get selected again if necessary. So 2,000 to 10,000 resamples are commonly used. For many statistics, it takes quite a bit amount of computational time. So let's go ahead and bootstrap on our arsenic list. Looks like I've got it already set up. So we got the one sample list in, how many, and then the bootstrap, that's a direct carry forward from the last time. And this one, you see it all working, I think pretty independent of the data science module. So this is what went on in data science module. And then finally, we're going to go ahead and do the 100 interval estimates and get information from them. So let's see what happens. Please work. And while that's doing its thing in the background, let's suppose that this was the result of our bootstrap. There's our value of 19. And here are the intervals, and we have quite a few failures. 1, 2, 3, 4, 5, 6, 7, 8. So that would be a 92% success rate, which actually does correspond to our actual interval probability based on the binomial distribution. And either of those would give us a way to generate interval estimates. And I will let that thing do its stuff in the background. And let's move on to confidence intervals for the mean value. So we can also compute intervals for population means. And these are appropriate if the center of mass of the data is the statistic of interest. Intervals symmetric around the sample mean are most often computed. For large sample sizes, symmetric interval adequately describes the variation of the mean regardless of the shape of the distribution. That's because the distribution of the sample mean becomes closely approximated by a normal distribution. And when you get your statistics class, that property is called the central limit theorem. And it holds for data that follow any distribution that has finite variance. In other words, if the variability is bounded, and you take enough samples and compute a statistic on those samples, that statistic will appear to be normally distributed. For smaller sample sizes, that won't necessarily be the case. As skewness of data increases, more data required. And for really skewed distribution, it can take as many as 100 observations before the mean is sufficiently stable to be unaffected by the largest values to assume this distribution is symmetric. So let's go through the classical way of doing it. The symmetric confidence interval for the mean are computed using a statistic called the T statistic. And the T statistic is just a different distribution data model. So we've seen normal, log normal, Gumbel, log Pearson. I think those are all the ones we've talked about. Oh, and uniform distribution. There are other ones. One of them is called the T, and it's well documented in the statistics literature. And so an interval estimate of the population parameter for the mean is to take the sample mean, x bar, take the sample variance s squared, divide that value by n, how many things are in the sample, take the square root of that, and then we're going to multiply that essentially a sample standard deviation times the quantile associated with the t function at probability alpha over 2 for n minus 1 things in the t function. So the t function has a couple of arguments to it. And then for the upper limit, we take that mean value, we add the t function at the 1 minus alpha over 2 n minus 1 level multiplied by the sample standard deviation. The critical values on the t distribution are either looked up in a table, that's the old-fashioned way of doing it, but now that books no longer are relevant, we compute them with the t distribution quantile function. And so if the sample size n is 25, then we would get the quantile from the t distribution of 0.025 and 24, and the quantile of the t distribution 0.975 and 24, which happen to be minus 2.06 and plus 2.06. And then the width of the constant confidence interval is a function of these critical values. And naturally, there is no example there. We're getting close to lab time. A few other confidence intervals which are undocumented as of now. Asymmetric confidence intervals for means. Bootstrap for means with small sample sizes, highly skewed data. Confidence interval for variance, non-parametric, parametric. Confidence interval for quantiles, and then the rest is prediction intervals. So the idea is pretty straightforward. We're using a statistic determined from our sample to estimate an interval that will contain the statistic from the population, and we can control the probability of being wrong. So if we want our probability to be wrong to be really small, our interval gets really big. If we can accept higher probability of being wrong, the interval becomes smaller. And you will be doing this in other classes in the future. And they may have a more confusing way of explaining it than I've done, although I really don't think that I could get any more confusing than I have. I believe I have a 95% confidence that I have confused you all thoroughly, and I'm not worrying about it. But in the background, just bear in mind the bootstrap example. In some level, that's all that's really going on, is you're constructing an interval according to a formula, and that interval has been shown by bootstrapping by other people way smarter than us that 95% of the time it will contain the population value if certain criteria are met. And then bootstrapping is actually preferred to other methods because it's non-parametric, but it comes at a price. The price being, especially on a new data, is we've already seen almost 9 minutes of computation to do something that we can do in a fraction of a second if we just use this formula. Okay, that is all I have for today as far as the lessons are concerned. I'm going to stop sharing my screen. I'm going to hand it over to Farhang, and actually this is the first time I ever got it early, so that's good.
Second time this semester.
Well, at this rate, maybe there'll be a third time. You are now the host.
Thank
And
you.
maybe take a 4-minute break.
Yes, exactly. Let's begin the lab at 11:20. So if you want to go and have a break, please do. But bring back your brains and your memories because we're going to need them.
Dr. Cleveland, I have a question. Did you get my email I sent like a day and a half ago or so?
That'd be a
Can
yes.
you hear me? Oh. You did?
Yeah. I haven't replied to
Okay.
it yet, but I got the email.
Okay. What did you think?
I'll reply. It'll be along the lines of what you suggest.
Okay. Thank you.
Oh, this is recording. I don't want to go read my email. Never mind. There we go.
Dr. Cleveland, are you there? Yes, not. Okay, it is 11:20, so let us begin the lab. Today we're going to talk about A/B testing and confidence intervals again. So who wants to tell me what is A/B testing and when do we use it?
Is it when we're looking at two distributions and trying to determine whether or not they come from this two samples, and we're trying to determine where they come from the same distribution?
So we are looking at two samples, but what are those samples? Like if I'm looking at a stream flow data from Mississippi River and from Colorado River, will that comparison be an A/B testing?
No.
Then what is A/B testing?
Randomized data from the same scenario.
What do you mean same scenario?
Like from the same river? Kind of spitballing here.
Okay, moving back to what we discussed on Tuesday. What example did we use for A/B testing? Is Jordan here?
Yes, I am here.
Okay, so do you remember the example of A/B testing that we used on Tuesday?
I do.
What was that?
Well, I know that my button had a 3% decrease and button B had a 3% increase. So I decided to switch to button B at the end because I didn't realize how big the margins were.
So you took the role of this stubborn seller who wanted to keep the old design and resist the change, but eventually we used A/B testing to prove that if you change to the new design, you're going to make more sales and get more clicks.
Yes.
Okay, so this is A/B testing. We use A/B testing to control almost everything else about the situation and assess the impact of a certain change, in the case of our previous example, change of the design of the add to cart button. And then it's basically a hypothesis test to see whether the group that sees the new design is behaving differently from the group that is seeing the old design. This is the general idea of A/B testing. So in our first example today, first, do you know what this, do you know this logo, this Daily Planet?
I do.
I
Yes.
recognize it, but I don't know what it is.
Awesome.
Where
So,
Clark Kent works.
the Daily Planet newspaper is a fictional broadsheet newspaper appearing in American comic books published by the DC Comics. So it comes up here and there, and commonly in the Superman books. So this newspaper is considering switching from the Times Roman font to the Times New Roman as an attempt to make it easier for their audience to read the newspaper and hence increase the online purchases. If you want to know the differences between Times Roman and Times New Roman, here are some of them. You see how tiny these differences are. So someone came into their office and consulted them and told them that if you do this, you may be able to sell more. So they have prepared two versions of their newspapers, one of each font. On the first day, they had a total of 1,398 visitors. Randomly, half of them, which is 699 visitors, saw the original version with Time Roman, and the other half saw the alternative version with Times New Roman. The first group purchased a total of 175 copies of the newspaper. This number was 200 copies for the second group. Based on the observations of the first day, first, calculate the purchase rate for each group, and then decide whether the Daily Planet should change their font in order to increase the online engagement time. So, what do you think we should do? What kind of problem you think we are dealing with here?
This feels like AB.
Why?
The same population, but one thing changed between the two samples.
Okay, and now that we have identified we are dealing with an A/B testing kind of situation, what should we do? What is the approach?
Make a graph.
Why?
So we can visualize the data.
So we can compare and see which
So,
one's better.
okay, make a graph, visualize the data, compare. What are you trying to compare?
The two fonts, I guess.
You
We're
want to try,
comparing-
you want to compare the fonts?
We're
Here,
comparing
this is,
Or
the
when we
purchase rate.
compare the visitors that the fonts get,
Purchase rates.
purchase rates. Okay. So you are comparing the behavior of your two groups. The first group that was exposed to the original version with Times Roman, and the second group who was exposed to the alternative version, which was the Times New Roman. Now, based on the numbers here, in each group, we had close to 700 visitors. The first group had 175 purchases. The second group made 200 purchases. If you were the business owner, would you like to switch or would you like to keep?
So we're using just the purchase rate on the first day to determine whether or not we switch or not.
We need to do some kind of test, which is called A/B testing. But currently, simply based on the numbers, would you say we should switch or would you say we should stay? Currently, I have 4 answers on switch in the chat box.
Probably switch, but maybe run some more tests.
So based on this piece of information, you would say switch.
yes,
Even you, Jordan.
even me.
Okay, so you thought you learned your lesson from the other time?
I did.
All in for the change. Okay, so Abdul is asking, are they gonna do the test only one day? That is a very good question. No, but currently you have the information on day 1. And me being me, I'm pushing you to answer my question and make a judgment based on the first day only. So do I have anyone in the room, in 41 of you, who would say that you should stay with the original font? So Jordan the stubborn, Brandon the brave, you are also switching. Awesome.
I mean, we only know one day, so, you know, just seems like.
So Brandon is staying. Okay, we have one for the other team. Let us go on and run some tests. So for day 1, I have 699 samples in my group 1, 699 samples in my group 2. Group 1 purchased 175 copies. Group 2 purchased 200 copies. So for me to calculate the rate, I am going to divide number of purchases by the number of samples in that group. And that is going to give me a rate of 0.25 for the first group and 0.29 for the second group. So, Brandon, do you want to change? It seems that your second group is doing better. Do I have anyone who wants to change their opinion?
Nope.
No.
Okay. One moment, guys, sorry. Okay, sorry. Then I'm going to call the man-Whitney U test from the Skippy stats, and I'm also importing NumPy. I am getting a distribution of zeros and ones for my first sample set and 1 for my second sample set. And then I'm running a man-Whitney U test. What is a man-Whitney U test? What kind of test it is?
Doesn't it?
Parameterized.
Come again?
Non-parameterized.
Non-parametric test, yes. What is the use of a non-parametric test?
It's like in case if your distribution isn't normal distribution, I guess. Like
Okay,
that.
flash review. We introduced 3 types of statistical tests to use so far. What were they?
Determining whether the means are the same.
Give
Determining
me
whether
the name. Give me the name of that type of test.
Gaussian, and
Nope.
then
Skew.
Nope.
Shapiro-Wilk.
Nope.
the type.
So, do you remember when we were talking about hypothesis tests?
Yes.
Okay. You have already named some of the tests, for example, Man-Whitney, Shapiro-Wilk, and stuff. These are belong to bigger umbrellas. We have 3 big umbrellas of hypothesis tests. Abby is saying parametric, non-parametric. So 1 umbrella for parametric, 1 umbrella for non-parametric. What is the name of the other umbrella? Say that and you can come under my umbrella. Ella, no, binomial, no.
Experimental.
Again, that is the name of a distribution. Come again?
Experimental.
No. Is this normal?
Null hypothesis.
No. Pay attention to my question. Is this normal?
What are you asking? What is normal?
How do you check whether something is normal or not normal? With the normality test. Yes, Jalissa, thank you. So, 3 umbrellas: normality tests, parametric tests, non-parametric tests. What do we do with normality tests?
Check to see if it's normal.
Exactly. We run them to check if something is normally distributed or not. When do we use parametric tests?
When we're looking at the statistics of the sample or the population itself, like let's say what are the means are the same, stuff like that.
Okay, yes. We use parametric and non-parametric tests to compare different groups and see whether they are significantly different or not. Okay, that's what we have learned so far. But when can we use parametric tests and when can't we use parametric tests?
It can be used when the data is normally distributed.
Yes. So if we know that our data is normally distributed, we can use parametric tests. Otherwise, we can't. We have to stick with non-parametric tests. Okay, now, what kind of test is Mann-Whitney U?
Non-parametric.
It's a non-parametric test. So what is its goal?
How do you
Check
know
to
it's
see if
not-
they're in the same distribution.
Yes, we are checking to see whether they are significantly different or they come from the same distribution. So why am I using Mann-Whitney test without testing for normality?
Is it because a null hypothesis test isn't normal?
It's because Mann-Whitney U test is a non-parametric test. And as Harper said, it has no assumption on normality. Okay.
So we use the parametric tests when we know the normality.
Exactly.
So let's say we know it tells us it's not normal. So we use non-parametric. But if it tells it is normal, we use parametric.
Yes. Even if it is normal, you are still able of using non-parametric tests. The only limit is that if it's not normally distributed, you cannot use parametric tests. Okay?
Okay.
So we run the test on our, please could you explain the meaning of a rate? What are you talking about, Abby?
I think she's talking about that
Oh,
placeholder
that's
you have.
Abdul, sorry. Could you explain the meaning of rate? Is it something in my code?
It's in the print statement.
Oh, here. So in this statement, I want something like this to be written. And this 0.3f means that I want 3 numbers after my decimal point. It is working like a placeholder.
So 3 sig figs basically?
Yes. Yes. So if I change this to 2, it will give me this. If I change this to 4, it'll give me this. Okay. Now, we run the Mann-Whitney U test for the null hypothesis that B is less than or equal A. And we get a p-value of 0.066. Is this a small p-value or a large p-value?
Large. Because
Do I
it's
have any
bigger
other
than-
answers?
It is bigger than 0.05.
Okay, so you're comparing it with 0.05. Where did you get that number?
That's the usual generalized. We compare the whatever we're given.
Who am I talking to?
Wally.
Wally. I am the owner of the Daily Planet newspaper. And I'm paying you a lot of money to do me some analysis. You go, get some data, you come back to my office, and you tell me that I got a p-value of 0.066, and it's a large number because I compare it to 0.05. Should I just accept that number from you?
I suppose no.
So where is that 0.05 coming from?
It's the significance level.
It is alpha or the significance level. What does it mean? So when you choose 0.05 as your significance level, what does that tell me about your confidence level on your test result?
We're 95% confident.
Okay, so Wally, this is what you need. You want to come out and say, I'm 95% confidence, or we are 95% confident that the rest of the statement. Okay, so you want to compare 0.066 with 0.05, and you're telling me that it's bigger. What does it mean? When you get a p-value greater than your significance level, what does it mean?
It would be the probability that they're both different then.
Are you rejecting the null hypothesis, or are you failing to reject the null hypothesis?
The thing is, we fail to reject.
When you get a p-value greater than your significance level, you fail to reject, which means that you are accepting the null. What was your null? The null hypothesis was that B is less than or equal A. So you have to accept that. B is less than or equal to A.
So that would
You
mean that
shouldn't have switch. So
I have a question.
yeah,
So
I can't hear you.
we did 1 day, right?
Uh-huh.
How does the function or whatever know that B is less than A?
So here I'm creating a distribution of zeros and ones. How many zeros I have? 699. Then I replace 175 of those zeros with a 1. So for every person who had made a purchase, I put a 1. The rest of them will have a 0. The same thing for my sample B. So I'm basically comparing two distributions of 0 and 1s. And I want to see if they are significantly different or not. According to the test that you just ran, they are not significantly different. So as the person who is going to make the call, you should stay with your original font. Did you get the answer to your question? Hello. Okay, I got a yes in the chat box. So how many of you have decided to switch?
I'm not switching.
You did switch, man. I remember your vote. So I'm just not sure if Brandon switched at the end or not, but he was keeping the winning team at that point. So after a week, they had a total of 10,086 visitors. Randomly, half of them, 5,043 visitors, saw the original version with Times Roman, and the other half saw the alternative version Times New Roman. The first group purchased a total of 1,072 copies of the newspaper. This number was 1,190 copies for the second group. Based on the observations of the first week, first, calculate the purchase rate for each group and then decide whether the Daily Planet should change their font in order to increase the online engagement. So, based on these numbers at the end of the first week, how many of you are staying? How many of you are switching?
I'll
I
stay.
will stay. Oh, I'm switching to Times New.
Vote in the chat box. I have 2 that are switching. Okay, Abdul is staying. Jordan, are you staying or are you leaving?
I am staying.
Okay. So how many votes for staying? 2? Everything with me is a trick. So let us move on. Let's create our samples. Group 1, 5,043. Group 2, 5,043. Group 1 purchased 1,072 copies. Group 2 purchased 1,190 copies. I'm calculating the rate, and I'm getting a rate of 0.213 for Group 1 and 0.24 for Group 2. Seems that Group 2 is doing kind of better, but the difference was larger before. So I'm creating my distributions and I'm running the test. And for the null hypothesis of b less than or equal a, I'm getting this p-value. Is this a big p-value or is this a small p-value? What does it mean for you?
It means that
What does it mean to you?
we reject the null hypothesis
Why?
because the p-value is less than 0.05.
Okay. So your p-value is less than 0.05. So you decided to reject the null, which means
That we should have switched.
yes, which means that b is greater than a and you should have switched. Okay. Any questions? Jalissa, it really depends on your call on the significance level. So if you are comparing it to 0.05, you are 95% confident. If you are comparing it to 0.01, then you are 99% confident, and so on. So Jordan, after making all the wrong calls in the business world, you have just decided to go into sports?
Yep.
Okay. Good luck. After a month, they had a total of 42,000 visitors. Randomly, half of them, 21,000, saw the original version, and the other half saw the alternative version. The first group purchased a total of 4,300 copies of newspaper. This number was 5,700 copies for the second group. So you see that the gap is quite large now. Based on the observations, do the same things and say whether they should switch or not. Let's ask for another vote. Are you staying with the original font or are you switching?
Okay, so this is in between 4,300 and 5,700, right?
Yes, in groups that are 21,000 each.
Okay, okay. I'm going to switch.
I respect the attitude. Keep trying. Yes, that's the winning spirit. Okay, do I have anyone who wants to stay? Brandon. Even Brandon is switching. Okay. Wally, that's the entire thing about the business world. You're always being tricked. So, Wally is staying. Interesting. Let us move on. 21,000, 21,000, 4,300 group 1, 5,700 group 2. Calculating the rates, and we are getting 0.21 and 0.27. So group B is doing way better. we create the distributions, we run the test, and we get a p-value of 0, which is small enough that you can confidently reject the null hypothesis and say that B is a better alternative. Switching the phones really helped. Finally. Okay. We did work on an example with 3 sample sizes over 1 day, 1 week, and 1 month. And we ran tests and we saw how having more samples will give us a better tools to pass a judgment on a hypothesis test. Do you have any questions about what we did, why we did it, and what we concluded from it?
Can you say that again?
Do you have any questions about what we did in this example, why we did it, and what we concluded from each step?
I'll ask, what does alternative mean? Like, what does alternative equals last?
Alternative means the other option. So what your initial font was the Times Roman, that is your A. Your B or your alternative is to switch to Times New Roman.
I suppose.
Aaron, we basically made conclusions at every step. In the first one, we said that the p-value is not small enough, so we concluded that we should have stayed with A and not switch to B. For the second part, we had a p-value of 0.002, which was small enough, and we said, okay, B was the better option. And then in this one, we got a very small p-value. Let me see. Very small p-value, and we were very confident to say we should switch to B. So those were the conclusions. Any questions? Okay. Now let us move to our next example, which is on confidence intervals. From a normally distributed population, we randomly took a sample of 100 adults with a mean height of 165 centimeters. Suppose the standard deviation of the population is 8. What is the unit for this 8?
I think it's sigma, right?
Not the sign, the unit. It is sigma though.
It's a square. Wait, no.
It's the same unit as the rest of your data, which is centimeters. Okay. Now, the first question asks, what is the estimated true population mean for the 95% confidence intervals? So, question, what we have here, this 165 centimeters, what is this?
The mean,
Mean of?
the height, the
Of-
population.
The mean height of the population?
I think
That's
it's
one
sample.
answer.
It's from the sample.
It's a sample. I lied.
Okay, cast your votes in the chat box. Who says population? Who says sample? What do you mean sample plus population? That's cheating, Wally. It's like voting for Biden plus Trump. That's not going to work. So, what you have is the mean height of your sample. Because first of all, if you read the question, it says from a normal distributed population, we randomly took a sample of 100 adults with a mean height of 165 centimeters. So it's literally telling you that it's about the sample. Second of all, you're still in the man world, so you don't know much about the population. You're trying to infer some information about the population based on your sample. That is why it is asking you, what is the estimated true population mean for the 95% confidence interval based on this sample? And then how about 90% confidence interval? How about 99% confidence interval? So, hoping that you remember something from Tuesday, what are we trying to do here?
We are trying to find the true population mean,
Mm-hmm.
and we're trying to create an interval of where we think it could fall 95% of the time.
Yes, very good. How do we do that?
By doing this, we find the populations, the sample mean, and then we create a interval of the sample.
How did
And
we
then-
create that interval? There was one specific statistic that we calculated.
Margin of error.
Yes, MOR or margin of error. In order to calculate margin of error, what do we need?
The standard deviation.
And
Do we need a variance?
no, when you have the standard deviation, you kind of have the variance, but you don't need that.
Can you give a hint?
Sample size. And one more thing.
Do we need multiple samples?
You have a sample. In this case, it has 100 adults in it, so your sample size is 100.
Yeah.
The third thing that you need is
Z-score.
Yes, Z-score associated with that specific 95% confidence interval or others. Okay, let us move on. Step one, organize the data. How many samples we have?
100.
What is X bar?
165.
Why?
It's the mean.
Yes, that's the mean of your sample. What is a standard deviation?
8.
Given to you. And these Z-scores. So the Z-score associated with 95% confidence interval is 1.96. For 90, it's 1.645. And for 99, it's 2.576. How do I know this?
The Z table.
The Z table. Where do you find the Z table?
Online.
Google.
In your statistic book.
Google.
Okay, tell me what to search for.
Z table.
And then click images.
I like that. I agree.
Where to go?
That looks great. The first one. Yes.
Oh wow.
So give me the Z-score of 95 based on this table.
Maybe we need a better table.
See?
Wait, did you say a Z-score of 0.95?
Oh, wait, of like 0.9954. That's
Kinda.
1.7.
So it's hopefully it's right. 0.8289.
What?
Wait, you said look. Wait. What was the question again?
I want the Z-score for 95% confidence interval.
Oh, okay. Sorry, my bad.
It could be in between 1.6 and 1.7. Probably more on the 1.6 side.
Would it be between 1.6 and 1.7 or 1.6 and 1.5?
I think 1.5 is too low for that.
Alright.
So probably 1.6 would probably be your best bet.
So
1.7
1.5 is associated with 0.9441. 1.6 is associated with 9545. So if you're looking for 0.95, it will be in between here.
Wait, isn't there a 0.9505?
Come again?
Is it
Oh, I was
0.905?
looking at 0.0.
At 1.6 and 0.05, there's a 0.9505. Can we use that?
This one?
Yeah.
Yes, you can. Why not?
I have a question.
So-
What does the top mean? Like, what is that?
What do you mean by top?
The 0.01, stuff like that. What's that for?
Oh,
Yeah, because it seems like you're looking all the way under 0.05, and I was looking at 0.0. Does it really matter where you look?
to be honest, I think as long as it lands you to the closest z-score, it doesn't matter. But looking at these, I'm seeing that you're getting slight changes in that specific digit. So
Because if the if the first row is supposed to be the z-score, right?
the
It
first
has z.
column,
Yeah.
yes.
What is the
That's
top
the
source
z-score.
represent? So they're both representing z-score.
Yes, yes. For all of these numbers in the row, you will get a z-score. But depending on what percentage you are looking at, you may have to do some interpolation between these numbers. If you see the number that you want in that table, then you're good to go. If it's not there exactly and you want to be very precise, you may want to do interpolation between two numbers that your number falls in between. Yeah.
So I guess when we are looking for the z-score, so it doesn't really matter where we look because they're kind of all relatively the same. Like 1.4 is 91, 92 is pretty much in between 91 and 93. So is that okay for us to just choose from that, or should we just Google what is 95?
I would do the second way because I'm lazy and that's easier. And when you do that, just cite the source that you're using and you will be good to go. Dr. Cleveland says top row is portion beyond left column. So for example, if you are looking at a score of 0.002, then you will come to the third one and look at this column.
Oh, okay. Okay, that makes sense. So I guess we're looking at it correctly.
Wait,
So
if
I
we're
guess,
looking at
so then we would need to be like, if we're looking for I forgot, we're looking for like 95. So then we would just stay in the 0.00, right?
0.00.
So okay, so we were talking about it was supposed to, oh, now it's a different one. Okay.
Yeah, I'm just trying to see if there is something better that we can use.
What about the one? Yeah, that one.
Yeah, like right here. What is so it's showing that the two numbers matter, the 0.2 and the 0.05. What does the 0.05 and 0.2 mean?
So since we have time, we can actually go and look at this. So a z-table is a table that tells you what percentage of values fall below a certain z-score in a standard normal distribution. The z-score simply tells you how many standard deviations away an individual data value falls from the mean. It is calculated as this. So it has to do with the mean of your distribution and with the standard deviation. Example 1, the score on a certain college entrance exam are normally distributed with a mean of 82 and a standard deviation of 8. Approximately what percentage of students score less than 84 on the exam? So we're going to calculate the z-score. based on this equation, it will be 84, which is the number that the question is asking for. It's our x, minus 82, which was the sample mean, divided by 8, which was the standard deviation. So we do the calculation, we get a value of 0.25. Then we are going to use the z-table to find the percentage that corresponds to that z-score. So what is the first significant digit in this number?
2.
2. So you come to this column and you find 0.2. What is the next significant digit?
5.
So you go here and you find 5. So now if you move in this row and in this column, you will find a number that is associated with 0.25.
Oh, that's it? Oh, never mind then. I guess that makes sense.
I'm going
Pretty
to
straightforward.
put this link in the chat box if you are interested. And
Oh, so if we're looking for 9.5, okay, that makes sense. Oh, so we were way off. It's more closer to 1.96
yeah,
than
that's how I usually do it. You can just search for z-score confidence interval and get something like this. Easy, huh?
Yeah.
It is now.
So use Google. Google is your best friend. So z-score for 95, for 90 and 99 is written here. On step 2, we are going to calculate the margin of error, the MOR. Do you remember the equation for MOR?
I believe it is z squared times the, don't know what that is, over the square root of the sample size.
That is our sigma. That is the standard deviation multiplied by the z-score divided by the square root of our sample size. Thank you.
Yeah.
So that's how we calculate our margin of error. Then we are going to calculate the margin of error for 95% confidence, 90% and 99%. Why I have to calculate them separately?
Because they're all different confidence intervals.
Even though my standard deviation and sample size is the same, the z-score associated for each one of them is different. So the margin of error for 95% confidence is equal to 1.56. For 90%, it is 1.3. For 99, it's 206. What kind of relationship you see in these 3 lines?
The margin of error increases, actually no, yeah, increases over time.
Over time?
No, over the bigger the confidence interval, the margin of
So
error.
as you increase your confidence, your margin of error increases. Does that make sense?
kind of.
Yes.
So let's say that I stand 20 feet away from you, right in front of you, okay? And I give you a ping pong ball. And I say, I will give you $1,000 if you can hit me with that ping pong ball. Okay?
Okay.
So not only you get to hit your TA, you're going to get paid for it. This is awesome. So in which case would you feel more comfortable? If I allow you to hit me only on my body, or if I tell you that even if your shot gets within 1 feet of my left and right, I will still give you the money.
I'm not really confident on that because I can't throw.
So
Second,
between the two, which one do you prefer?
I prefer it being 1 foot near you instead of actually hitting you, because a ping pong ball isn't really good at, you know.
Exactly, because the more margin of error I give you, the more confident you are that you can make the shot, right?
Yes.
That's why by increasing the confidence percentage, we are getting a larger margin of error. Does that make sense?
Yes.
Okay. Now that we have calculated our margin of errors, we are going to find the estimated true populations for each one. So X bar minus margin of 95, X bar plus margin of 95, and the same for 90 and 99. These three statements are the results of our work. The true population mean will be captured within the confidence interval of 163.4 and 166.6, and the confidence is 95%. I will be less confident if I shrink this range, and more confident if I expand the range. Are we clear? Water,
Yes.
mud, wine.
Honey.
Okay. So we took another sample of the same size, and this time the mean height was 167 centimeters. How does this new piece of information helps us in getting closer to a better estimation of the population mean? Our previous estimations were only done based on one set of samples. Now we have another one. We have a second sample of the same size, and we are getting a new sample mean. Is this good for us?
Yeah.
Why?
Oh, why we took another sample size?
Why is it good for us?
Because sometimes it's possible that we have to compare and make sure that the information we got from the first sample isn't just an outlier or once in a time thing.
The very simple reason for it being better is that you're getting a second chance of understanding your population. So always more samples makes us happy. Now, let us move on. We are going to modify the code cell with the new information. We are going to calculate the margin of error again, and we are going to get this statement now. So in this case, you are saying that you are 99% confident that the true population mean is somewhere between 164, basically 165, and 169. So within this window of 4 centimeters, you are 99% confident that you are capturing your population mean. Am I right?
Yes.
This is based on the second sample. Based on the first sample, you were 99% confident that you were capturing that between 163 and 167. So one range from sample one range from sample two, you put them together, the area between my these two fingers has a higher chance of capturing that true mean. Correct?
Yes.
Okay. Any questions?
I do not believe so.
Are we all clear? Are we all happy?
Yes.
Okay. Now, for your exercise, I've asked you, why do A/B testing? What are the important steps of A/B testing? And think of a few mistakes that you think may cause your A/B testing to go wrong. And make sure to cite any resources that you may use. Okay, if you have no questions for me, that will be the end of the lab for today. And while I'm going to stop sharing, I'm going to ask Dr. Cleveland to give you a brief review on information about next week's exam, as many of you seem to think that it was today. Those of you who wanted the exam to be today, if you want, we can give you an exam.
It's quite all right. I'm okay.
So, Dr. Cleveland, you are the host and the room is yours.
Okay, so exam number 2.
Your voice is kind of low.
Of course it is. Built-in microphone. Oh, I know what the problem is. Better when the microphone's plugged in? Yeah.
It's all good now.
Exam 2 is on Tuesday, the 30th of March. It will cover lessons 10 through 16. So randomness, sampling, empirical distributions, descriptive statistics, our data models, and hypothesis testing. The exam will be structured just like exam 1. There'll be an in-class component and a take-home component. Other than that, there's nothing to add. We will notify you of a workshop sometime this weekend if you want to come and ask questions or go through some of these parts in the context of what's likely to occur on exam number 2. And on Tuesday during the lecture portion, the 10 o'clock to 11:30 will be a review component for exam number 2, mostly just to prime you for the in-class part. And then everything else behaves the same. And next Thursday, we do yet another conceptual shift and look at some more elaborate aspects of fitting data models to data.
Okay, so is the test going to be over? Just make sure it's over lessons 10 through 16.
Well, since interval estimates occurred in lesson 16, yes.
Okay.
Yeah, you'll have to write a bootstrap simulator for a gamma distributed variable with a non-symmetric lambda and a beta term. Just kidding.
And some data gathering as well.
Yeah, you'll have also, we need to write a web scraper. So you go out to websites and scrape appropriate data in order to make your hypothesis test. No, we're just using jargon that came off jargon.com. It will be very much like the laboratories and the homework assignments. And as with those, you'll have full access to the mighty internet, including the dark web. We'll do dark web enabled searching because most of the Russian hacker websites have elegant solutions to everything that we're likely to ask. So we'll take up any further stuff on next Tuesday, and then we will schedule sometime this weekend for a workshop.
I have a question. Is there a exam review exercise thing you can do? Like, let's say problems we can work on to prepare.
Well, you've been doing them. You've done the homework problems and the laboratory examples. So if you've done all those, you have reviewed for the exam.
Makes sense.
But no, there will be no fake exam because that's just a pain in the butt for me. So it's not going to happen. How long should we expect the take-home portion to take? Well, Quentin, as usual, you have 24 hours, so it'll take 36. But the take-home portion is doable in less than 24 hours. And it is indeed best to wait until 20 minutes before it's due to open it up and start it and attempt it. Because nothing we ask is hard. And 20 minutes should be more than enough time. I'm also kidding again. A couple hours sounds about right. And if you schedule your time appropriately, you can, the way I would take the exam, since you'll get multiple submissions, is I would download it when it first becomes available, look at it and do any of the easy problems first, export that solution, upload it to the server so I have a non-zero content in the server, and then go back and start working on the harder problems, and then at the last possible minute to do a final upload that. Or you can wait till the last minute and do it that way. So danger is, the D in danger is silent. Doesn't that spell anchor? And then you have to go manage that, right? Danger management. Who's Danger's middle name? Is that Austin Powers? I think that was his middle name in the original movie. Any other questions? Okay, good. So we will see you on Tuesday. There'll be, the exam on Tuesday will not start until 11:30, the in-class portion. From 10 to 11:30 is a review period. So that would be the time to ask any burning questions other than what's the second question of the exam and how do you do it? Because I won't answer that. Because I don't know what the second question of the exam is. I won't know until a couple minutes before it posts. Because I kind of make these things up as I go at the last possible minute. Because if it wasn't for the last minute, nothing would get done. Anything else? All right, well, very good.
May I say something, please?
Absolutely.
So, unfortunately, even though I repeatedly told you to make sure that you understand everything about your lecture notebooks, lab notebooks, and exercises, I think many of you, at least some of you, didn't really feel comfortable with this stuff on the first exam. I really hope that you have a better understanding of the exam wipe. Something that I wanted to really point out is that do not leave a question empty. Even if you think that you cannot answer it 100% correct, try to work on it and get some points on that question. When you leave something completely empty, there is no way for me
That's a zero. But
exactly.
if you put something,
I will at least know that you know this has something to do with NumPy, for example.
yeah, I mean, don't put something completely stupid like cats are fun as an answer. That will probably earn a zero if that's all that's there. But make some kind of attempt. Nobody ever does it, but it would also be quite appropriate if you just write out an algorithm or a pseudocode. That counts for something. That will help us understand that you mostly understand the question, but you may not be able to actually script it. That's not a zero anymore. That's a non-zero result. That is worth something.
Yeah.
I have a question.
Sure.
What does pseudocode look like?
Looks like words.
Yeah.
Is it just me writing out what I think in a paragraph form or what?
It's like you writing instructions for a person who's 4 years old and doesn't speak your native language, and you want to tell them how to make a peanut butter sandwich. So it's very precise instructions, but it's not necessarily computer code.
So it's like me saying import NumPy then use the mean function, blah, 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 blah. And I can just go like that.
Let me tell you this. We are going to read the data first. We're going to calculate descriptive statistics such as the mean and the standard deviation. Then we are going to use the standard deviation and the mean to check for different distribution data models. We're going to use a plotting position formula to get the empirical CDF, things like that. You're explaining the steps that are necessary for that specific problem to be solved, even though you're not writing the code.
So here is an example from the mighty internet of pseudocode examples. And this is fairly detailed pseudocode, but
yeah,
he's providing, we do a test. If something's greater than or equal to 0, if the test passes, we write pass. If it doesn't pass, we write fail. Next thing is to set something equal to 0, set the grade counter to 1, and then while the grade counter is less than or equal to 10, do stuff. So that's all pseudocode is it's a high-level set of instructions that would eventually get translated into actual code. Let's see if I can find some other examples. How to write a pseudocode. So this is actually still fairly specific. So it's telling you we're going to do some test, and then if the result of the test is a 1, we're going to print a response. If it's not a 1, we're going to print a different response. So that's all that a pseudocode would be. Here are some of the key things. You don't go to a lot of detail and control structures. Sometimes you have to. Keep it simple and keep it concise. This particular example, indentation, white space, they're doing that because they're trying to build a way for the code to write itself. So if you started with this as a pseudocode, you could go from that to Python or C++ pretty quickly. And then you can get elaborate. There are some fancy pseudocode standards. I was going to see, let me see if I can pull up an example of some Fortran pseudocode, because that might help enlighten things. Okay. Pseudocode 4 and 5. Here we go. The overhead camera running. Oh, I know you can't hear me. Get the overhead camera running. I'll show you example of pseudocode. Video overhead on. That did not autofocus very well. Let's try again. So I'm not sure how well that's showing up. So up here, this is the pseudocode for the example that I presented back when we calculated the mean of 5 things. So here's what the pseudocode is. Set the sum of values to 0, set a counter to 0. As long as the counter is less than 5, read the data value, add it to the sum, add 1 to the counter. when you've completed step 3, so the count is no longer less than 5, divide the sum by 5 to get the average, print the result. So there's what it looks like in pseudocode. And then when we convert that into actual programming language, that pseudocode naturally gets a bit longer. See if I can. So there's program code, there's pseudocode. So pseudocode is a way of writing out steps that you're going to need your program to do. And literally you can write pseudocode in your notebook and then go back and start filling in the parts and then make the pseudocode the actual comment statements. So that's all pseudocode is. If you were expecting it to be something more dramatic and exciting than that, you were sadly mistaken. As you gain experience, so in 15 years, you will be able to write fairly complicated scripts, if that's what you end up doing, without having to lay out pseudocode initially. But until you're there, trying to do scripting without having a roadmap in the form of pseudocode is really hard. You're all lucky in that when I was taught programming back when dinosaurs roamed the earth, we had to draw flowcharts for every damn thing. And that is an inefficient way to write code. So literally what we did back in the day was you'd write out pseudocode, then you'd convert it into programming language, you get the program to run, and then the last thing you ended up doing is we draw out the flowchart and hand it in. So usually the last thing we did was draw the flowchart, so it was pretty crappy when it got handed in. And I lost many points on flowcharts because I thought as a documentation tool, they're excellent, but as a design and build tool, they are a monumental pain in the butt. So my flowcharts went something like input data, do computations, write results, end. And that was an insufficient flowchart for getting through amateur computer science. So I switched to engineering where you didn't need to do that. And now, what, 30 years later, I'm learning it all over again. So any other questions before we hang up and end the call? Because we're now, oh, actually, we're good on time, aren't we? We're way good on time. So I have no way to get out of here.
I actually do.
Sean?
Did somebody just
do
say
have
something?
A question. On the last exam, that very first script, the one that counts for like 1 point, what did that do? Because the moment I ran that, everything went belly up. Like Python, the notebook stopped working, so I had to like export it to an online kernel. And
That first script,
yeah.
first cell was something like that.
We can't see your screen.
Oh, well, that makes, oh, then I can tell you anything I want. Let's see, share screen. So the first cell looked something like that, not exactly like this, because I made some changes so that I think it'll run on both Windows and other ones. All that does when you run it is it reports back the host name of the computer you're working on, the username of the computer that you're working on, and then some information about the Python subsystem you're using. So we use that as a way to help us debug your work if we get to that point. More importantly, and I hate to reveal it, but I will, if we get 2 PDF files in that happen to have the same host name, the same username, and the same Python subsystem, I will automatically assume that a copying event occurred, and neither of those 2 exams will get graded with anything bigger than a 0. And if you want to, we can go fight with the powers that be. Because the likelihood of 2 people having the same host name and same user ID is very low. And actually, if it's an online host name, it's really, really low. So you said it cratered your system. Let me go see if that is indeed true. I will go ahead and try to run this on Windows version, remote, but I got to get to the right one. Okay, so I'm connecting to a Windows version of Anaconda, or Anaconda if you want to pronounce it correctly, but I like to put the R at the end of it. I drive a Toyota and other things. My father-in-law, who's long passed away, he put an R at the end of everything. He would have made a great pirate. Get that, R. He was a native Texan and talked extremely funny, in my opinion. And my wife is his daughter, and she picked up that. Let's see if I can get this thing to, there we go. Can you let me load it? So I'll go to Anaconda. I don't know what any of this, I must have clicked on something that's trying to cancel that. Come on. Takes a little bit for it to load up, and now I'm really going to challenge it. I'm going to resize it, and it has to go through a whole bunch of conniption fits on the resizing. So I'm glad you brought that up because I need to test this anyway, so I'll do it in front of everybody or make a fool out of myself, either of which is a fine outcome. And there we go. So loading environments. It's really struggling. It was working earlier today, which is something that you all get accustomed to seeing. Well, it was working until it had to.
That's how it always goes.
So now I am replicating what I think most of you have. I think most people in the class are using a Windows machine. Some of the Macintosh people are stuck with an Apple product, which you've already paid for, so you want to get your money's worth out of it, but don't buy a new one. And it will be loaded up any minute now. Should be playing music, but we'll get a copyright strike on the video if we do. I wonder what happens if we whistle it. I wonder if their algorithm is sufficiently sophisticated enough to be able to detect me whistling.
I hardly doubt it.
Well, it is owned by Google. They're becoming the new evil corp. By the way, there's a new seasons of that series coming out pretty soon. So watch your Amazon Prime notes. Okay, so finally, okay, so now I am running on my remote computer, and if I run that, hopefully it just ran. Oh, poor little network's having a rough time today. Okay, that's the cell block I want to run. Interesting choice of words there, Dr. Cleveland, cell block. So we're like in a jail. So on a Windows machine, here's what I get. So the host name I'm running on is EC2 AMAZ-RNSPJS0. So that's sitting in a server farm in Ohio. My username is EC2 AMAZ-RNSPJS0/administrator. My Python subsystem is located in C users administrator Anaconda 3 Python exe. I'm running Python 3.8.5. It's a 64-bit AMD 64 build. I'm at system information, major systems 3, minor 8, micro is 5. It's release final. So if you were to turn in a PDF file with ECA2 AMAZ RNS PJS0 administrator, I would assume that you had directly copied this, and we could go to town on that. You could attempt to prove otherwise. That's what that first part of the code is. Those of you that have Windows, does it work as is? Because these are all Linux type commands, and I'm not sure. I mean, I'm running in a Windows operating system, but I'm not sure if it transports directly.
It works on the labs. It's just on the exam, like, because I work backwards up.
Oh.
Yeah.
So next exam, run that code, that first code cell first, and then do the exam, because that's an easy point. All you got to do is run it. If it errors out on you, leave the error there. Don't worry about it, and then do the rest of it.
Well, I mean, I had skipped the question, but like once, and I had most of it done, but like the moment I hit that, I did that very first script, it just like Python was unresponsive.
Yeah, I would suggest you don't do that next time. What I would do on an exam is once I have my whole exam built the way I want it, I would go ahead and go up to the run, and I'd choose run all cells, or actually restart the kernel, run all cells, either thing, because that way I know I have a complete clean run. And you let it go through its thing. The other nice thing it does is it gets all the cell run numbers in order. So that comes up as a 2. There's a hidden cell that was the first one. And as it runs down, it shows all the cell counts. So cell number 9 is where it stops. Mine has an error right now. I don't have the data science module installed. And so the rest that isn't going to happen. But that would be how I would do my final run of the notebook.
Okay. All right. That makes sense. I didn't know if there was like some kind of like clear all variables button.
There is, but it's not a button. If you want to clear your notebook, you can do the, actually, let me go, I'll do it right here. The % symbol, the word RESET, and if you do that, it's going to bring up a dialog box and say, you're going to destroy everything. Are you sure that's what you want to do? And they use nicer words for what I just said. And if you put a yes in, you have wiped your namespace completely. A reset is to be used very carefully. Don't get in the habit of it, because you will unintentionally destroy stuff you don't intend to. If you don't want to interact, I think if you put the dash F switch, that's the equivalent of typing yes. And it has reset everything. Let's prove that. I am going to, let's create a variable. My name equals Freddy Krueger. Okay, so I'll run that cell. And I'm going to go to this cell below the reset because the reset now is overridden. And I type my name. Sure enough, I get Freddy Krueger back. Now, if I reset the whole sheet, if I type my name's not defined. So reset is rather dangerous. I've used it 2 times this semester in our lessons, and I kind of blew by it, and nobody asked questions, thankfully. But it's a way to completely wipe a worksheet. Any other questions on magic functions?
I'm good.
Yeah, there's a few other magic functions that we will not get to, but you may see Farang or myself use them from time to time when we lose control of our notebooks. That's what we're doing. We're basically either the exclamation point symbol is sending a command to the operating system shell. The percent symbol is sending a what's called a magic function command to the Jupyter Lab namespace. Both of them are well documented on the mighty internet and are used from time to time as necessary. So for instance, we can use a shell command called, see, what is it? It's dir. That should return the directory of my computer. So I'm currently in directory C users administrators CE5362. So I shouldn't be in that directory. That's a monumental screw up. I have a program called untitled.ipynb workshop 1 and workshop 5. I wonder if I can change the directory to actually, I forget how change directory works in Windows, so I'm not even going to try. I'll do it this way. Go to my desktop, Jupyter files. We're in lesson 17, so I think that may have changed the we'll bring up lesson 17, which we've already run. And now if we run a cell, actually I need to import the operating system first. Done. Now I can do a dir, and it tells me that I am in C user administrator's desktop, my Jupyter files, lesson 17. There's a preamble script, and I could try to run everything, but we already know we're going to get a bust as soon as we hit stuff that needs. Okay, so let's stop here because the next thing will cause a error message. Let me add a few cells. So let's pick a name of something. We have something called box df key X. And we've returned that. And now if we do the violent command of resetting, if it will let me have another computation cell, thank you. Do a magic function, force the reset. So now what do you think will happen when I attempt to interrogate the box df key X? We're going to get the pink screen of you screwed up. Box df is not defined. So that is ways to violently regain control of your spreadsheet. of your notebook. The other way, you know, up here, you can interrupt the kernel when it's running. You can use this do it all over again, which is a restart. Often when you lose control of your kernel, if you can't enter a reset, your best bet at that point is to literally exit the program and restart it, because that forces a complete rebuild. Hopefully I'm sharing my screen right now. Other questions? Other than that, we will I think we should add that to the next exam. Write the MTUS function.
Yikes, that's not.
Mute the mic, taunt at PC, unmute the mic, smile. That will come in handy in a political career as well. Mute the mic, taunt the voters, unmute the mic, smile, continue. Promise them anything, deliver nothing. You will be a successful politician in any country, not just the United States. That applies anywhere in the world.
Well, if this engine doesn't work out, go into politics.
Yeah, I suggest that if this engineering gig doesn't work out, your next choice is business school. And if that doesn't work out, political science, and then off into the big leagues. Because all you have to do is have frequent flyer miles and you're good to go. And they're kind of good for our national morale, because no matter how bad a day you're having, you can always blame it on a politician somewhere, and nobody is going to try to calm you out of that. Like, yeah, they're all jerks. So you're good to go. My college roommate was a bodyguard for Arnold Schwarzenegger for quite a while, and his comment is, of all the people I bodyguarded, he was the best, but he was still a jerk too. They're all jerks. All right, that's all I have. And you have lab over the course of the weekend. If you want to prepare for the exam, go through the homework exercises. Don't go through a whole homework. Pick an exercise out of it that seems likely of something that I would ask you on an exam, and convince yourself you can do it. More importantly, save a copy of it somewhere, so in case something very much like it does show up on the exam, rather than thinking, you get to apply the miracle of
CCMR.
Correct. And if you cut and paste your own stuff, you don't even have to do the one of the C's. Copy, modify, run. Very good. Let me go ahead and exit out of this guy. See, file, log out. I will now possibly exit my Anaconda build. And I'm going to exit my AWS instance. And what we were just running, part of why it was slow is look how much RAM that is. That's pretty much the same amount of RAM that's on this guy. So it's as if I'm paying Amazon Web Services to run Windows on a little teeny microprocessor just like this. I'm going to stop sharing. And wow, a lot of you stuck this out. Well, congratulations to y'all. That is kind of scary, actually. We will announce a Saturday workshop. Is Saturday a good day for you?
I think so.
It will probably be late afternoon, 5-ish, but we will send you an email message to that effect along with a link. Jordan says I have to get math. I forgot everything because I switched from coding to OCam. Yeah, I can't help you there, Ms. Torres. Just when you go to the store and you see stuff advertised as organic food, do you scratch your head and go wonder how many carbon bonds there are in that?
No, who eats organic food?
Well, if you did, it's all organic. Pretty much everything that they sell in a grocery store has carbon bonds in it. So it's a bad naming convention, and it comes from California, where I come from, the land of nut cases. I was able to get out of there and get to Texas when I could.
Good for you.
Many aspects of it were a good decision. I have to confess, I miss the weather where I grew up and the real estate where I grew up, but I couldn't possibly afford the real estate where I grew up now. So maybe with their economy cratering, and if California runs everybody off and then go broke because they can't tax anybody anymore, the prices of property will come down to something realistic, and I can move back there to grow old and die. Any other questions? I'm going to hang up then.
Take care, everyone. Be safe.
Okay, everybody, have a great weekend. I will have this video and last time's video posted by the end of today. And expect an email announcement on a weekend workshop. Bye-bye.